Hello and welcome to Lecture 2 of Chemistry for the Interdisciplinary Sciences. Today we're going to have a look at the nucleus. Instead of looking at the electrons, which is what we were looking at in the last lecture, we're going to think about the structure of the nucleus, what we can tell about the nucleus from the periodic table, and how the nucleus can change, which we're not going to see very much of in this course, except for this one lecture. So let's have a quick look then at the learning outcomes. We're going to define the term isotope during this lecture and learn about average relative atomic mass. So find out that some atoms of some elements weigh more than other atoms of the same elements. We're going to have a look at the arrangement of protons and neutrons in the nucleus and figure out how you can tell what they are, and also find out about the ratio of those two things and how that affects the stability of the nucleus itself. Finally, we can find out how unstable nuclei can rearrange themselves into more stable nuclei, and we're going to write some equations to show that. So let's just start off with this elemental symbol that we've kind of seen before. We've got neon here in the middle. The capital Ne there is the chemical symbol, we say. So whenever we see a capital N or a capital letter, that's telling us that we've got a new element. And then sometimes it's followed with a lowercase letter because if you look at the periodic table, there are more elements than there are letters. So we have to use some symbols with two letters in them. So here, Ne, neon, we have the proton number at the bottom, which is the number of protons in the nucleus. And the atomic mass at the top, that's the total mass of a nucleus of this type of neon. And that'll make a little bit more sense in a second. So if we were to figure it out then for neon, how many protons, neutrons and electrons there are in the atom, well, first of all, we'll look at the proton number and we'll notice that it's 10. So the number of protons must be 10. That makes sense. We mentioned this idea before that anytime we got a positive charge, like a proton's positive charge, if there are 10 of them, it must attract 10 negative electrons over there. So that's what that's going to look like, 10 negative electrons. Now, if this element has a mass number of 21 over here, then that suggests that there must be 11 neutrons, because if the mass number is the total mass of protons and neutrons, then we can take that mass, 21, subtract the number of protons, which is 10, down there at the bottom, and that tells us that this particular atom that we're seeing the symbol of here must have 11 neutrons. Now, remember that I said that the neutron's job in an atom or in a nucleus is to hold all those protons together that are positively charged. They're trying to repel each other away, but the neutrons there are interacting with the protons using a really strong nuclear force there, holding them all together. So that's the job of the neutrons. Think of them a bit like glue. The protons there are governing how many electrons there are, and the electrons are getting into those different energy levels, the different orbitals we talked about in the last lecture. And again, we saw how their chemistry can be affected by how many of them there are as they build out. So let's just quickly test our understanding of that one. Scandium. Here's a scandium elemental symbol. So let's just start with saying how many protons are there in a nucleus of a scandium atom. So if you want to answer the question on top hat, please do. I'll give you a second to pause and do that. Okay, so scandium has the proton number 21 down there, then the number of protons is 21. So the correct answer here is A. Let's just get ourselves a lovely pen. There we go. So A, 21 is the correct answer. How about how many electrons are they? So again, let's have a quick think and have a pause. So in an elemental atom, there are as many electrons as there are protons. So again, we're just looking at the proton number 21 and we're saying, oh, yeah, it's 21 again. Hopefully that makes sense. Finally, how many neutrons are there? Well, the total mass of this atom is 45. So let's have a quick think. Okay, so it's going to be, there are 45 total particles in this nucleus, or it weighs 45. Remember we said that the relative weight of a proton and a neutron was 1. We're calling each one 1. So here there are a total of 45 particles. 21 of them are protons. That means that B, 24 of them must be neutrons. Now, again, as I said, the number of neutrons in there can be really variable because it's just glue that holds together the protons. You can have lots and lots of it or not very much of it. And so sometimes the number of neutrons in a nucleus is kind of variable. It's just as long as it's stable, it will have that many nuclei. Now this shows up on the periodic table with some of the mass numbers in the table not being full whole numbers, not being integers. Now, if we were to use the method that we were using before, we'd say, okay, there are 17 protons, with 35.5 total particles. Subtract one from the other, we got 18.5 neutrons. That doesn't make any sense, does it? So, in fact, what must be happening is there are several different types of atom of chlorine. Now, by definition, the nucleus of the chlorine must contain 17 protons. That's what defines it as chlorine. However, it can apparently have 18 neutrons. Perhaps it's a mix of 18 and 19. Maybe it's a mix of 18 and 20, and there's just loads more 18s than there are 20s. So if we have a quick look at the periodic table, you can see that quite a few of them are not whole integer numbers, especially if you look in the D block there, that's the middle part, scandium, titanium, vanadium, and so on. All of those in there are not round numbers. They have a decimal point there. And so that suggests that there are lots and lots of different masses of nuclei which have the correct number of protons. These are called isotopes. So these are nuclei with the same number of protons but different numbers of neutrons in there. So, why? What does that mean, really, is the question. So let's have a look at this. So, in general, a nucleus wants roughly even numbers of protons and neutrons. And you can see that there's a sort of straight line in this axis. What this graph is showing is how stable the isotopes are. So in the black in the middle, and let's just quickly draw that line, there are lots and lots of black atoms there in the middle that are very stable. You can see there's the 1-to-1 proton to neutron ratio, so it's not exactly the case that it wants equal numbers of protons to neutrons, but that's a roundabout correct. And as the atom gets bigger and bigger, it's able to accept more and more neutrons in the nucleus. Then you see that the next colours, so we got sort of the green and blue here, these are not at all stable. And in the middle, all the red and yellow colours in the centre. So this is just in case you can't see the colours. In there, those ones are very stable. So we've got very stable in the middle and then less and less stable as the atom moves away from those roughly equal numbers of protons to neutrons. And again, you can actually see that line and see how it changes as the proton number increases. So it's kind of a bit like if you were making a sculpture out of lollipop sticks or whatever. If you use too little glue, that's unstable. If you use too much glue, that's unstable as well. And we have the exact same thing going on in atoms. So you can see that there's lots and lots of different ones. For each row here, that's a different element, isn't it? It's a different number of protons. So down at the bottom, there's only a few. There are only 3 different isotopes of hydrogen. So you probably already, hydrogen. That is just one proton. If we pop to the periodic table for a second, up in the top left there, hydrogen, 1, 1. 1 proton, and the total mass of the nucleus is 1. Therefore, it's just a proton all on its own. But if you add a neutron to that, you get an isotope called deuterium. And if you add another neutron to that, you get a very unstable isotope called tritium. So there can be lots and lots of different masses of any given nucleus in there. And again, it's just because of variable numbers of neutrons. There is a widening gap, and you can see that as we go up, it seems like there's more and more nuclei which are stable. If you see the distance of all the different nuclei in that section, for instance, compared to the different nuclei in this section, there are much fewer. So you can see that there's lots of different stable isotopes for many elements. So how do we figure out? The thing is, we want to know, if I weigh out a gram of sodium chloride, for instance, that contains sodium and chlorine, I do want to know how many atoms I have there. And I'm not going to be able to know how many atoms of a specific isotope I've got. So what we display instead on the periodic table is the average relative atomic mass. So what that means is taking into account the masses of all the different isotopes and their abundances, we can start to figure out what the average atom will look like. And so it looks a little bit like this. It's the sum of the relative abundance. When I say relative abundance, I just mean percentage of atoms that are of a certain form. So for instance, if all carbon atoms, you might have heard of carbon dating before. Most carbon atoms on Earth anyway are made of carbon-12. So that is 6 protons and 6 neutrons. If we have another quick look at the periodic table, carbon's well worth learning. It's there in the second row in group 4. So it has an atomic mass number of 12 and a proton number of 6. That means it's got 6 protons and 6 neutrons. But there is also carbon-13 being made in the sun all the time. And that carbon-13 gets blown out from the sun. It gets trapped in the Earth's magnetosphere. And it slowly mixes into the carbon dioxide and the carbon cycle in the Earth. So the amount of carbon-13 at any given time in the atmosphere and in the carbon cycle is around about equal. And then as that carbon gets removed from the carbon cycle, so for instance, is involved in a fossilized bone or a shell or something like that, then it no longer has the normal fraction of carbon-12 to carbon-13. And because carbon-13 is semi-stable, it will itself decay. We can have a look at the ratios of carbon-12 to 13 to find out how long something has been out of the carbon cycle, i.e. how old something is. So in a carbon atom, and this is the approximate fractions of the different isotopes of carbon here. So we're saying that 99-ish% of all the carbon atoms are carbon-12, 1% of them are carbon-13. If that's the case, then the relative atomic mass that we see down here at the bottom, so this is what I'm calculating at the moment, we say, okay, it's 99% carbon-12, so that's sort of the first isotope, and that would be this bit here. And then this bit is the second isotope. And because we've only got 2, we can kind of stop there. So we take the percentage of carbon-12 and times it by the mass of that particular isotope. So carbon-12 weighs 12. And then there's 1% carbon-13. So we add those two together and we come up with an average mass of a carbon atom is only very slightly over 12. Which makes sense because 99% of all the atoms I said were carbon-12. So they should weigh 12, around about. So this is how we calculate the relative abundance. In the workshop, you're going to have a look at some examples, especially chlorine. Chlorine's very interesting. So that's in the third period in group 7 there. It's Cl chlorine under fluorine. That has the atomic or the average relative atomic mass of 35.5. Now, in fact, it's made up of 2 different isotopes, chlorine-35 and chlorine-37. And so you can figure out what the relative abundances must be of 35 and 37 in order to give you an average relative atomic mass of 35.5. So that's going to come up in the workshop, I'm sure. And it's a really nice little example of a sort of thought experiment you can do to say whereabouts it is. So what happens then when you have an atom that is very much not got equal numbers of protons and neutrons, or rather isn't on that line of stability that we've seen before? So you probably have a smoke detector in your house, and if it's quite an old one, it might use an isotope of americium, americium-241. Americium so named because the Americans and the Russians were racing to discover it, and the Americans really wanted to rub it in. But here we've got americium with 95 protons. So that's what defines americium as an atom there. It's a nucleus with 95 protons. And what does that mean? It has 146 neutrons in it. Quite a lot more. And what it does is it slowly decays all the time. So it's slowly changing its nature and giving out some particles. In this case, alpha particles. So we're going to have a look at those in a second. But it's giving out those alpha particles, and they go to the detector, and whenever the detector is detecting alpha particles at a normal rate, everything is absolutely fine. However, when smoke gets in the way, all of a sudden the detector is no longer seeing those alpha particles come towards it, and so that's what starts the fire alarm from ringing. The smoke there being a lot more dense and having a lot more matter than the normal air. So I mentioned that there are some types of particles that a nucleus can give out. Now the nucleus, like americium, if we just pop back there, has a lot more neutrons than protons. It has two choices really of what it's going to do. One of the things that it can do is it can undergo alpha decay. So I'm just going to disappear for a second so we can read this. We've got alpha decay is where the nucleus kicks out what we call an alpha particle. Now if you have a look at its symbol, that's an alpha 4, 2. So if the mass number is 4 and the proton number is 2, then we must have 2 protons and 2 neutrons, which is basically, if we have a look at the periodic table at helium up on the top right, notice that it is also 4, 2. So up there, right at the end of the periodic table. So an alpha particle is just a helium nucleus. Helium is very, very stable. We already talked about that before in terms of its electronic structure, but it's also got a very stable nuclear structure as well. So it's a helium nucleus. Now, this alpha particle is quite big as it goes. It's a whole atom that gets kicked out of the nucleus. You can imagine that that's a very, very high energy reaction that has to happen. It's got to kick out that entire nucleus, 2 whole protons and 2 whole neutrons, and that thing is going to leave that atom at very, very high speeds. So it's quite a damaging form of radiation, really, that very high energy particle just colliding with whatever it comes into contact with can provide a lot of energy for chemical change of that substance. And so if that chemical was DNA, for instance, you can see that changing the DNA is bad news there. So alpha particles don't tend to travel all that far. They're the least penetrating form of radiation. And by that I just mean that as it travels, it's absorbed by air or paper or something like that. So one way that a nucleus can make itself more stable then is to kick out a helium atom from its own nucleus and then rearrange. If a nucleus has kicked out 2 protons, has taken them out of its own nucleus, then it must have changed what element it is, because we define the element as the atom with the right number of protons, if you want. We define elements by the proton number. So that's one possibility. The other possibility is that the nucleus tries to change a neutron into a proton. If we've got too many neutrons, as we did in the last case, too many neutrons, well, we'll just swap one into a proton instead. And when that happens, what we have is beta decay. Now, a beta particle is basically just an electron. And hopefully that makes sense to you, this idea that if a neutron, which is neutral, turns into a proton, which is positive, in order to even out charge in the universe, it has to also create a negative particle too. This is called a lepton. Those of you doing physics, you can really start to think about the nature of protons, neutrons, and electrons. For us chemists, we're just going to accept that a beta particle is an electron. It's a really, really high energy electron. Now, it's less damaging because it's just a teeny tiny electron as opposed to the whole nucleus of a helium atom that we saw before. And remember again, electrons are about 1/2000th the mass of just one proton. Never mind 2 protons and 2 neutrons. So it's more penetrating than an alpha particle because it's smaller. It's less likely to collide with anything. And you can absorb it with something like an aluminium plate or something like that. Now, why is this useful? Well, we already talked about americium as being a nice little way of detecting smoke, but we also use unstable nuclei in things like nuclear medicine. So for instance, if you want to find out where your new medicine goes in the body, what you can do is label it with a radioactive isotope of something. So for instance, iodine is quite a common one to make radioactive. And you basically just put the body into a machine that can detect these particles, or the higher energy version of it, the gamma particles that we don't have to do. And you basically just look at where in the body is giving off this radiation. So let's say I am inventing a drug for a pancreatic disease. If it all collects in the pancreas, that's brilliant. It's doing exactly what it's supposed to do. If it collects a little bit in the pancreas but also hangs out in the brain, that's probably not going to be a viable candidate for the rest of the medical trial that you're trying to do. So radiochemistry is quite interesting, and what we're going to have a look at now is What is an atom once it's undergone decay? So this process is called fission. So nuclear fusion is where you put nuclei together. Fission is where one nuclei splits into two parts, really. So here up at the top, we've got americium 241. It's got 95 protons in there and a total mass of 241. If that gave out an alpha particle, so if it removed 2 protons and 2 neutrons from its own nucleus, what would the new element that's made be? Well, we can start off by looking at the number of protons. So we look at the proton number, and we're saying if a nucleus had 95 protons and it kicked out 2 of them, how many would it have left? It'd have 93, wouldn't it? And of course, I've done the wrong side. So if we look at the top of there, we got 241 minus 4 is 237. So again, if it's giving out a total mass of 4, then it must have 237 mass units left. Sorry, I've done those the wrong way around. So there we go. We got 93 down at the bottom. 95 minus 2 is 93. 241 minus 4 is 237. So you can sort of think of this arrow here as a bit like an equal sign almost. 241 equals 4 plus 237. 95 equals 2 plus 93. And just try and keep them all even there. Now the last thing is, what on earth is this question mark going to be? Well, an atom is defined by the number of protons. So all we have to do is pop along to the periodic table there, and because it's ordered in proton number, it's going to be relatively easy to find. So we're looking for an element with the proton number of 93. That's right down there in the bottom block in the F block. And element 93, that's Neptunium. So that means that it must make a Neptunium atom, like that. Okay, let's do another one. I'm going to see if I can get out of the way. We got americium 241 undergoing beta decay now. Now I mentioned that beta decay is where a neutron turns into a proton. This is why the beta particle symbol has a proton number of -1. It's a bit weird, but it represents the creation of a new proton in the other substance. That's why it's a -1. Obviously you can't have -1 protons, but it represents the production of a new proton. Okay, so let's think. I must be doing the mass number, so let's do that. We've got 241 at the top, so 241 equals 0 plus what? Well, 241, doesn't it? So the mass number of this new atom is going to be the same as the one before. How about the proton number? Well, 95 equals -1 plus what? Well, it's 96, isn't it? So again, we're just balancing these numbers as they go along. And then again, we're going to pop to our periodic table. We're going to look at 96. Oh, curium. Brilliant. Curium, named after Marie Curie herself. And so the element is going to be curium there. So here, in these reactions, unlike any others that we're going to look at for the whole course, you see elements changing from one type to another through a high-energy process of nuclear fission. Okay, so let's have a quick look at another one. It is possible for a nucleus to break into a few different parts. Instead of just giving out that one particle, it breaks into 2 new nuclei and an alpha particle. And we call these nuclei the daughter nuclei. They came from the original. So let's start by asking ourselves, what is the mass number of the unknown element? So I'm going to let you pause and think about that for a second. Okay, so hopefully you've now written down the mass number up at the top. Let's figure out the proton number of that unknown element now. So again, you're doing the same thing, you're just balancing the equation each side of this arrow, which we're kind of imagining is an equal sign almost. So we've got 95 equals 18 plus 2 plus what? So again, I'll give it a pause if you need some more time. And then we're going to figure out the elemental symbol of the unknown element. So here what we're looking at is the element on the periodic table that has the same proton number as the one we've calculated. Okay, so hopefully you've done all of that together. Let's give it a go. So let's go back to the mass number. We have 40 plus 4 is 44. And, oh, that's going to be relatively easy, isn't it? 241 minus 44 is 197, I hope. So that's going to be the top one. We're going to have 197 at the top. And then we're going to do the same at the bottom. So I'll just write 197 to remind myself. Lovely. And then we've got 18 plus 2 is 20. So 95 goes to make an element which is 95 minus 20. That's going to be 75, isn't it? So that's going to be the proton number. Finally, we pop to our periodic table. Element 75. It's rhenium over there. So we must have rhenium. So let's replace that with something that looks a little bit better. The elemental symbol of the unknown element is rhenium. So this is americium splitting apart into a few different ones. And what I'd like you to be able to do is to be able to do some of these nuclear equations. So what I'm going to do now is show you a slide of some questions that I might ask you in a sort of exam environment, or your new tutor might ask you. And I'd like you to pause for a second, and then we'll do the answers next. Okay, hopefully you've paused. So let's have a look. We've got here uranium-234 splits apart into an alpha particle and some other element. So the first thing we're going to have to do is obviously figure out what the alpha particle is. So I'm going to try and draw the answers to these above or next to them. What's going to be clearer? Actually, what I'm just going to do, no, let's work through the first couple and then I'll show you the rest of the answers. So we've got an alpha particle is 4,2. That's easy enough. It's very difficult to draw with a mouse though. And the mass number is going to be 230 because I need a number that adds to 4 to give me 234. Okay, so then we've got 92 gives us 2 plus what? Well, this element is going to have a proton number of 90 then, whatever that is. And again, I'm going to pop to my periodic table, and what do I see? Oh, it's thorium. So thorium, TH. Again, don't worry if it took you a little bit more time than me to see that on the periodic table. You'll get used to where they are and how they move. So that's A then. This is it. Uranium undergoes alpha decay to make an atom of thorium-230, and that's how we describe an isotope, thorium-230. Okay, let's do the next one a little bit quicker. So we've got a beta particle is 0 minus 1. I'm afraid you do have to kind of remember that. If you can't remember that an alpha particle is a helium atom and a beta particle is an electron being given out. Okay, cool. And then we need to balance these. So 235 goes to make 0 plus what? Well, 235. So the top masses are going to balance there. 92 goes to make minus 1 plus what number? 93. Or rather, when I say go to make, I should say equals, if you want. And again, I pop to my periodic table, and element 93, we already saw that. It's neptunium again. Lovely. Okay. Oh, we're on a roll anyway. Let's do the next one. So we've got uranium-234 separates into a chromium-52 atom. Okay. So I'm going to have an element now that is 234 minus 52 is 182. Yes, 182. The proton number 92 minus 24 is going to be 68. Yes, 68. Lovely. And then we pop to our periodic table. 68 is europium. Europium. Again, if you can see that, just pop back to the periodic table, press pause, and have a go. Okay, so that's enough of my terrible handwriting. Let's convert this into something that you can actually read properly. So there we've got our thorium atom, our neptunium atom, and our europium atom. Now down here, the next question, uranium-235. So this time the mass number is going to be 235, not 234, there. So that's what we've written in the equation at the bottom. Uranium-235, there, undergoes alpha decay to make a gold atom of 197. So we knew the mass number of gold there. And what else? Well, again, you're just basically rearranging this equation and you end up with a sodium-34 atom. Pretty heavy as far as the sodium goes. I think sodium's mass number is 23. Don't know why I'm thinking. I can just look at the periodic table. Yep, there it is, 23. So pretty heavy for a sodium atom. Probably that sodium is going to undergo more fission. Okay, that takes me to the end of this lecture. Hopefully that made some sense, but don't worry, just feel free to ask questions in the workshops. That's what they're there for. And I'll see you at the next one. Bye.